All right. I'll just quickly peep into the chat room if there is anything that benefits our session. I think there is nothing happening there. I see people asking what is going on. What is going on is we have been trying to wait for your colleagues. Okay, I think let's get started. Can you hear me, guys?
Yes, we can.
Okay, I think we should now get started. Good if you can hear me. So let's get started. Oh, by the way, Malindwa notified me of your colleague who lost, I think, a father. I condole with him, and he had told me he was busy gathering, I think, some form of condolence messages in terms of contributions from you guys individually. So I requested him that he can take a break between 3 and 5 so that we could have the lecture, and then he resumes that collection after. So we talked about, we introduced ourselves to Power Series Solutions yesterday, and we looked at a couple of things. And today we are supposed to, I think we did all of this. Yes, that is all covered. And that, these are your exercises. There is something that we should use in what we are going to be doing that I needed to demonstrate. It's like we omitted a page. Interesting. Should be around here. Okay, I think it is this here. Yes, around here. Okay. So after this, there was some kind of it should have been like a remark or a comment. We have this exercise, but then we usually now attempt to manipulate some of these power series solutions, especially when we are faced with the differential equation. We'll find ourselves differentiating depending on the highest derivative of the given homogeneous or non-homogeneous equation. If it is second order, third order, or fourth order, you remember we discussed how we could get those solutions, and then we associated them with other approaches that called for linearly checking if the linearly independent solutions of that system can be used backward. Assuming you have one, then you could use to get the other. If you have three, if it is a differential equation and the highest derivative, it has three linear independent solutions, and probably you have two, then you could use those two to establish the third one. But now in here, it means that when we are given this series and you differentiate it depending on the nature of the equation you are dealing with, you will find that we'll have to manipulate these powers here. So here there are just some few examples that we are trying. We are saying here in practice, we have to combine series whose terms are not of the same power. So this is going to be key. Yeah? And we are saying in such cases, we make appropriate changes in index of the summation of the series, which do not change the sum of the series. So remember in what we did, the general representation of our power series solution, we had a sum which was an, and this was x minus x naught, and then this whole thing to the n. So usually when you have a second order or third order differential equation, it means you're going to differentiate this one, because now you can take this one to be your fx. If this whole sum is stated as a function, because you have an x minus x naught to the n. So if you have a differential equation of third order, for example, it means you have to differentiate this thrice. But when you differentiate it thrice, you must be mindful that by definition of the general representation of a power series kind of solutional function, when we defined it, we said it runs from n equal to 0 up to this is infinity. So it means when you differentiate this, you are going to have some n, then a n. Of course, this will be x minus x naught to the power n minus, this one will be minus 1. If I just try to differentiate this, you'll have n here. And of course, this will be f prime. So if we consider that, it would imply that in this in your differentiated function, now you can't run from 0. Why? If you run from 0, remember when you differentiate this with respect to x, this is n, this n here would bring problems. If you throw there a 0, this whole thing will vanish. So it means if this is 0, it means once you differentiate this, then you are going to run from n is equal to 1, not 0. So it means now there is an upgrade down here, whereby we will now have to sum from n will equal to 1. And if it was a second order, it would imply that you differentiate the original function twice. So it means that will be giving us n into n minus 1, then the other one will become a minus 2. So what I'm trying to say here is that if you do that, this term here changes, because you will now have, instead of n, you will now have in here, in between. I don't want to write the whole thing. So in here, from around here, you will now have, this will be n into n minus 1. That is what you will get in between. So since it is n minus 1, then into this and this one now will be n minus 2, because it will be n minus 1, which becomes n minus 2. But now when it becomes n into n minus 1, then an, then it means you cannot sum this from n equal to 2, rather n equal to 1. It means now you will start from n equal to 2. Because when you start from 1 here, it means that if you have 1 minus 1, it is a 0. Again, the second derivative. Now this one will be the second derivative. So f prime prime, it means for f prime prime, will start from n equal to 2 up to infinity. And this will help us to simplify. These would be complex kind of series that would emerge when we try to solve different orders of differential equations. Okay, now the same applies here. So for example, if you look at 1, if you are at 1, if you look at example 1 here, you can see on the left, we are summing from n equal to k to infinity. This is an minus k into x naught minus. So this is some would be general representation of what I've been trying to demonstrate here. Because remember, we will keep differentiating. So here, remember, it is initially 1 from our definition, but this k can keep changing. So if you have this and you want to get back here, because if we are solving, we'll always take it back to the actual definition, but we may be summing from different values of n. That is the would be starting point. So in this case, if we wanted to go back here, let me just illustrate very fast here. It means that I'll rub off this, just clear that one. Okay. So if we consider this general scenario here, if we have this sum runs from k to infinity of an minus k into that, but surely we can say that here if n is equal to k, but remember this is n minus k, we have to put a lot of emphasis on this here. It always starts there. So how do we shift from n minus k to n? We want this one to come back to this one here. That's the target. So we can simply think of a substitution. If we let, for example, if we say m, for example, if we say m is equal to n minus k, this is k. So we want to find n. What will n be? It means if m is n minus k, then it would imply that when you substitute here k, remember n runs from k. If you throw in k here, it means m is 0. But I'll put this, but m is actually n. Remember, we are just temporarily substituting this. So if you bear this in mind that our m is n, so if we say let m be n minus k, it means this power here, it is x minus x naught to the power m. But what does, if m is n minus k, it means when n is k, when you throw here k, m is 0. So this m equal to 0, this one here. Maybe I should change the color a little bit so that people don't get lost along the way. So this n, m equal to 0, is actually what is giving us this starting point here. You can see here we have n is 0. Remember I've said, but m is n. So m going to 0, it means now this n is equal to 0. So this has been now changed to n running from 0. But now when we say n minus k is 0, remember this is n minus k. If n minus k, m is n minus k, so this becomes to the power n, which is m. Remember I've said the m is n, so this becomes now n minus k becomes m, which is actually n here. But now what about this one here? You see here we are saying it becomes n. This is n minus k. So if it is n minus k, remember we are trying to make n the subject. So if you make n the subject here, what is n? N will be equal to m plus k. This is what you have. So if n is m, if you make m the subject here, sorry, m is n minus k. So what is n? N is m plus k. So if n is m plus k, it means in here where you have, remember it was an minus k, but n is minus k. In this case, we don't have to, since we have n minus k, this whole thing simply becomes m, which m is actually n, which is this one here. In this case, changing, rather making n the subject doesn't benefit us a lot, but we will see a scenario where this one also works. So if you do that, you can start from here and you end up there. That is that first scenario. Then we can also look at this second one here. If you consider the second one, we have, let me try to, okay. So in the second one, what we have? Here we have an minus 1. Now for this one here, how does this become that? So if you look at this, remember, we always, by definition, it is x minus x naught to the n. So here we started on the right to get the left. Here we must start on the left to get the right. Why? Because this is n. So assuming you had an expression which looked like this one here, then how would you go about this one here? Simple. One, of course, as we have demonstrated already, we have n minus 1. It always starts with a power, this power here. That's where things start. So since this is n minus 1, if we let m equal to n minus 1, that is this one here. Then the question is, what is, remember this n runs from 1. So since n runs from 1, then if we substitute, remember n is 1, and I've told you m is n. So if this power here is m, or if we say n is n minus 1, of course that would look bizarre. That's why we take it as m, but we know m is n. So if m is n minus 1, and you substitute, remember the sum here, this one here, it runs from n equal to 1. So if you substitute n equal to 1 here, it means m will be 0. That is why this one runs summation n equal to 0 to infinity. Of course, if you substitute infinity up there too, this is like change of limit. If you substitute n is infinity, of course, this whole thing will be infinity, because infinity minus 1 will give you infinity. Okay, now let's get to the other one. So this is now the part I had wanted to demonstrate in the previous example, but it did not.
Excuse me, sir.
Yes. I'm listening. Go on.
What exactly are we explaining? What exactly are we explaining? What are we talking about?
I don't know whether you've just joined. I am saying that if we are using a power series, let's say we have an equation like that, plus 2y prime is equal to, maybe this is a prime here, as this. If this is plus y, this is equal to 0. We looked at these equations and we solved these equations. But now when we have to solve this, assuming we have to solve this, sincerely to solve this using a power series solution, you are going to start with the definition. And we looked at the definition, and that's where I started. I said if fx is the sum. So instead of fx now here, it means y will be equal to sum n running from 0 to infinity. This will be an, then that will be x minus x naught to the n. It means you're going to differentiate this thing twice. You will differentiate, it means you are going to substitute this, differentiate this, That will be y prime. Differentiate the second time, you will substitute it here. Then y itself is this thing here. But be mindful that when you substitute into this lower limit is going to change. When you substitute into y prime, n will be running from 1 to infinity. When you substitute into y prime, this n is going to be running from, I've already demonstrated this. So if you do that, it means that, but remember when you are solving, you are going to have an issue of having different powers and then different indices. That's why we have started by saying here that in practice, this is where I started. Perhaps you are not following, young lady. That in practice, if we have to combine the series, because now these series are already combined, there is nothing uniform about them. Why? This one was initially to the power n, but when you differentiate this, now this one is going to be to the power here will be n minus 1. And you will be summing from n will equal to 1. Then what about the power of this one, which I also demonstrated? The power of this will be n into n, it will be n minus 2. This will be the power here when you have differentiated twice. And when you sum this, you are going to be starting from n equal to 2. So we are saying now you are summing series that are not the same with the powers. That's what we are saying here. That's what we are trying to mention somewhere here. That in practice, if you're summing series whose terms are not there of the same power, then the question is, how do you go? We are saying in this case, we make appropriate changes in the index of summation. So what am I doing? I am showing you how you can unify these indices. You can see that this index here, it has been reduced to this. And you look at this one here, it is now the same. So if you are rather, this one here is exactly the same as this one here. I think I should first rub off this for whoever asked you to follow what is going on. This here, this is exactly the same as this. Of course, there is a coefficient. The only difference is in the coefficient. This is n plus 1. Here, when you throw in this is a coefficient of n plus 1, and there is n plus 1, and this one. But when we talk of comparing or dealing with the sequences, rather series, the key here is the target is usually the power, which is this one here. This should be the same. And then you are summing from what to what? We are summing from n equal to 0 to infinity. Here we are also summing from n equal to 0 to infinity, and the power is the same. These coefficients here, these ones can be dealt with, because when you start to throw in the values of n, you know that these ones can be got. But if you are going to do this and you are going to compare powers, you cannot compare this with this one here. So what are we doing? We are understanding how you can make these indices similar before you actually try to solve. I didn't pick the name of the person who asked. I'm hoping we are now clear. Whoever asked.
Yes. Yes,
Okay.
we are clear.
I think now I can omit this one. You have already understood that one. It seems you are understanding, but you did not understand the rationale. Good. Okay, we can now continue. So since you've already got this one here, we can proceed. The same applies to this one here. So if you look at this, here you look at the power. This is again x to the n. This is running from n equal to 2 to infinity. Then the question is, if you have to solve this, how would you deal with this? Remember, this is x to the n plus 2. You see this one here, this one here. It is n plus 2, but this is not what we have in the definition. In our definition, we have to the power n. Of course, here it means x naught is 0. If you look at this whole thing here, this x to the n. it means x naught is 0. So what is the target? The target is to simplify it to something of that form. For n running from 2 to infinity, yes, it may have been 0, but you can see the nature of an. The coefficient which was an, it has already been upgraded to 3 into n plus 2 into an minus 2. So here it means you would be simplifying everything to that form, not this form, because our definition, it is here. It is an x minus x naught to the n. That's why I'm saying here x naught is 0, which is x to the n. But an, which is the coefficient, that is this whole thing, the 3 into n plus 2, then an minus 2. This is now the an. Once you throw in any 2, you will get that value there. All right, I think you've got that. So when we start solving problems, we should move faster because I have already preempted that. We will simply recall from what I have demonstrated here. Okay, so let's continue. Now we can look at a definition of what is analytic. Remember yesterday we took time to understand how you go about to get the radius of convergence and if you get a limit, does it converge, does it diverge? And then we looked at several examples, the ratio test and the root test that was based on reanalysis. Now in here, we have a few definitions that I'm going to demonstrate. Two things. One is to know if you have a function, is it analytic or non-analytic? Of course, for a function to be analytic, it means that function must be defined. If it is undefined, then it is not analytic. Then for any given point, it means that if you establish the point, of course, the point could be regular, irregular, and it could be singular or a non-singular point. We are going to look at what quantifies them or the classifications that we can use to deal with those kind of categories. And of course, those categories will be all based on the nature of that function in terms of being analytic or not. So here we are saying a function will be analytic at a point x naught if it can be expressed in this form. That was this power series form. This is the definition we have been using with a positive radius of convergence. And we said if you go through these derivatives several times, I've already demonstrated this, you'll end up with situations like this. But this one here, of course, will also be dependent on the nature of the equation. And sometimes when you differentiate, you may be forced to use the Taylor series expansion. That one will preempt further in the examples we are going to do. And here we look at some examples of analytic functions. These are quite obvious. They are far related to what you did in your engineering math 1. So there is nothing. That's where we discussed continuity, discontinuity, and you understood what a pole is. How do you remove a discontinuity? And as you go ahead and advance in your engineering, since you are doing civil, when they teach you things to do with stability analysis, you will revisit some of these things. So I will not dwell much on that. Okay, ordinary and then singular points. This one takes us back, but we can simplify it. So we are saying that a point can either be ordinary or singular according to the definitions. And what are the definitions? If you have a second order differential equation, this is what I started with demonstrating when that lady asked. And we have already looked at this equation 7. So from our previous semester, that is engineering math 2. If you have a system like this, and we are saying from this system, if you take this coefficient of y prime prime to 1, so you divide this by that. Generally, you divide this whole thing by A2. When you divide this by A2, you'll get A1 over A2, which is this one here. and then N naught over A2, which is this one. Now we are going to use this to understand what is ordinary and what is singular. So from this, we are saying a point x naught is referred to as an ordinary point if these two functions which are derived from these ones here are analytic at the point x naught. It means when you have x naught and you substitute it into these ones here, and those functions remain defined, then it means that point that you've substituted to maintain the nature of this function being defined will be referred to as an ordinary point. But if you substitute it and it gives it in an otherwise form, meaning it is not analytic, then it would mean that that is a singular point. So that is the distinction between those two. Okay. Then we can understand regular and irregular singular points. So here, what do we mean? We are saying if a point x naught is a regular singular point of the differential equation, that is the same equation here, the second order. So if it is a regular singular point, and of that singular point, remember from our definition here, the singular point is picked from, from our definition. Where is it? We had our fx, okay, here, equation 5. From equation 5, we have this, and our singular point is, it is picked from the term in the brackets. So the x naught here is the key. You remember yesterday we had the x, where x naught was 0, we had it as a 1, and we had it as a 2. And in those ratio tests, we are looking at the norm and how you can get, how you could get the range. And then we would say that range, if it is greater than the limit you've got, you would experience some form of divergence. And if it was less, you would actually achieve a limit that would be converging. So in this case, we are saying that if you have a regular singular point, and from what we have, that is when we associate that point with what we have extracted here in equation 8. Then if you deal with the substitution of that singular point, that's where we are saying here that if at least one of the functions in 8, this one here, this or that, is not analytic, then of course, if both of them, they are analytic, then this one, these two will be regular singular, the x naught will be a regular singular point. But if you deal with that same substitution and one of these is not analytic, or both are not analytic, then you will end up with an irregular singular point. So it's all about substituting those points in here. That will, of course, be based on the nature of the function A1 and A2, and you establish if this remains analytic or non-analytic. If it is non-analytic, you conclude that that point will be a regular singular point. And if it is indeed analytic, then it will be regular. Okay. Let's say an example. So from my example here, we can, let's just illustrate what I've just summarized, rather, what I have just said with an example. So we have an example here. This is a second order differential equation. And you can see we have x4 minus, this is now, I need to do some writing now. So this term here, that is x to the 4 to minus x squared. So this whole term here This is A1. Is it A2 or A1? I think this is A2. Then this whole term here is, okay, we have actually broken them down here. A2 is x to the 4 minus x squared. Then this is A1, and this whole thing here is A0. So these are the ones. Remember, we had A2 over A1, and then we had, we had A1 over A2, and then we had also A0 over A2. So what we are doing is what we have here, we are going to just substitute it directly into equation 8, this one here. The A1 over A2 and the A0 over A2. That's where I'm making the substitutions. So if you substitute into this is what you get. So A1 over A2, it will give you this one here. But this is evidently clear that you can factor this out. Difference of two squares, you'll get some x squared minus, and again, you break that one further up because there is an x squared minus 1, which will give x minus 1, x plus 1. That is what you will get here. Then A0 over A2, that is this one here. A0 over A2 over this one, that is this over this. This is a simple thing also. You will just, of course, if you look at the way we have factored this, it is 2x plus 1 over x squared minus. So the denominator is the same. Basically, it means if you have this up here, you have it the same denominator because this denominator is that denominator. So it means since this denominator here, x squared, so you have something like x squared, this is x plus 1. This is plus 1 here. But now you have this x squared, which is going to cancel with that x squared. And you have x plus 1, which will cancel with this one here. So from this one here, you'll only remain with a 1 over x minus 1 if you take this one here. Because you have x plus 1, which has cancelled with this one, then the x squared, which has cancelled. So you remain with the 1 here over that one. So that's what we get in here. So if we get this, that is 10 and 11. Now we want to check. We want to locate whether we can get these. What are they? Ordinary? Are they regular or irregular? So in attempting to do that, of course, we basically keep checking. One, are they analytic? So, or they are non-analytic. So here from, for example, 10 here, if you look at 10, it is obvious here that if you take values of x, for equation 10, you can see that for this to be analytic, x must never be a negative 1. Why? Because if you look at this x, if this x is a minus 1, then this whole denominator becomes a 0. That would be non-analytic because it will not be defined. Then if x is 0, there is x squared here, it will take this whole thing to 0. So it means that one also constitutes another point where this whole function here would be non-analytic. And of course, x equal to 1. Here you have x minus 1, x being 1, this whole denominator also disappears. You end up with that situation. Then what about for 10? Here in 10, x must never be 1. In the limit theory you did in your engineering math 1, you looked at these things. And these are what you call the poles. I think you did that with Mr. Kayondo Hassan. So in this case, x cannot be 1 because x being 1 would imply that this whole denominator vanishes, hence making this whole function here non-analytic. And those are the conclusions we are drawing here. That for 10, we are saying the function will be analytic. Is that okay? Except For 0, 1, and negative 1, which I've already demonstrated here. And for 2 here, I've already told you. For this one here, if it is 0, it will be analytic because you'll have 1 over minus 1, which is minus 1. That is if x is minus 1. And if x is 0, sorry, if x is minus 1, you'll get minus a half because this will be 1 over minus 2. Then if x is 1, if x is 0, you'll get a minus 1. But for this x being 1, surely it becomes non-analytic. So from that, we can just conclude that these points we have got here. But of course, in this, we also have this one. We are saying those points are singular points of the differential equation because at those points, those functions are not analytic. They are non-analytic or they are not defined. Then for us to know whether they are singular, irregular, or regular, we can just go ahead and then we deal with this and we substitute. Here you check for each of these points independently. So you consider minus 1, you consider 0, and then you consider a 1. That's what we are trying to demonstrate here. So we are saying to determine, that is this paragraph here, to determine which of the singular points 0, 1, and minus 1 are regular or irregular, we are saying that we can examine, we can, I'm trying to make myself a little bit comfortable. Apologies. Okay. So we are saying that to determine which of the singular points we have established above are regular or irregular, we can examine the functions. But recall that we said for us to, why isn't this responding? Okay. Recall that we have equation 9 here. You can see in 9 here, when we talked about a point being regular or irregular, we actually have this and this. So we incorporate what we have in our main definition. That was, I think, equation 5 or 9. Rather, I think equation 5. So we use this and then we use that. So we refer to equation 9 here. So what we have here is from our definition, 3.2. This one here. That's what we are using down here. Okay, somewhere here. Yes. So this is where we are. So to determine, we'll get the first one. This is x minus x dot. But remember, we have got 3 points, 0, minus 1, and 1. So when we test this one here, remember x naught is 0. So if our x naught is 0, this one is 0 here. If this x is 0, you remain with the x into this one here. And if that is the case, I think you recall that this thing was x squared up there. Hopefully you still remember. We had it as x squared into x minus 1, then x plus 1. So since we've got x, it will cancel with this power. That's what we have here. So this was x squared into x minus 1, x plus 1. So this x has cancelled with the power there. We end up with this one here. And we are concluding that this one, our conclusion is that this whole thing here is not analytic. Why? Of course, it is not analytic because here at x equal to 0, this whole denominator will disappear if we take in that value of x equal to 0. If this x is 0, this whole denominator vanishes, it becomes undefined. Then we test the second one. If we test the second one, you substitute, this is 0, it will give you x squared into that. Remember our denominator, This was x squared here. So this x squared will cancel with that. But there was, I think I need to write the other statement. The other statement is actually x squared. I know some of you people who are engineers, but grammars, it is a problem. This is x plus 1. This is what we have. This is just the denominator. So when you look at this denominator, which is a simplification of the x to the 4 minus x squared, please try to mute yourselves, okay? If we have x to the 4 minus x squared, which is this, the x squared goes, so this will go with that. Then you have the x plus 1. This, you have x squared into that x squared. Remember, this is a square here. So x naught is 0. So this one becomes x squared. So it is x squared into x squared. That is x plus 1 over this one. So 1 over the x squared goes with the one in the denominator. Then the x plus 1 goes with this x plus 1. You remain with the x squared over that one. Okay? So from what we remain with, which is this one here now, remember we are at 0. We are at x naught. We check both of these at x0. So at x0, this one will give you 0, and that will be over minus 1, which is 0. This one is analytic. That's why we are saying that this one is analytic or defined at that point. Okay? Then we can conclude, we draw a conclusion for the 3 points, but the first one, which is 0. And we are saying, we conclude that that point is an irregular singular point. Okay? Why irregular? Because here it is analytic, but here it is not analytic. Remember we said if...
What is analytic?
Guys, try to mute yourselves. Can you behave and you mute yourselves? Molindwa, put your house in order. Mr. Molindwa, you need to organize your class. Or if you are failing, then you call on I don't know whether she's now your deputy, Madam Sony. Okay, let's not get distracted by the people in the background. I know not all of you are attending, rather paying attention. You can hear people in the background are talking. Okay, so if you substitute into this, we are saying this will be, here we conclude that in this case, the point is irregular. Why? Because one of these has turned out to be non-analytic or undefined. But if both were defined, then we would conclude that it is a regular point. A regular point, but this one becomes irregular because of that. Okay. We can now look at the other part. What goes on next is exactly what we have done here. The difference is this one was for x is equal to 0. Now we try for x will equal to 1. And then we try for x will equal to minus 1. That is the x naught. So it means in the first one we did, it was, where is my pen? It was x minus x naught. So in the first one, we had x minus x naught, but x naught was 0. So we had x just. That's why we substituted and we got x squared. Now, when we come to x is equal to 1, it will be now x minus 1. So it means instead of having x squared here, since this was 0, this will be now x minus 1 here. So you have x minus 1 that you are going to square. Then what you get, you are going to multiply it with this thing here, without, of course, this one here, when that one is not there. So that's what we are going to demonstrate. And once you do that, you again do the same analysis. You substitute the value x will equal to 1, and you see if it perishes or if it does not perish. Does it remain defined or it remains undefined? Okay, so that is the part you see now here. The function, of course, by definition, this is it. But remember, I've told you now the x naught is 1. So that is the x minus 1 here. Because our x naught is 1. Then the first one, when you substitute, you get this. Remember, our denominator is x squared into x minus 1, x plus 1. So the x minus 1 has cancelled. Hopefully, please bear in mind that this denominator, we factorized it and we ended up with the x squared, which was x minus 1, then x plus 1. This is the denominator we have. So since this is the denominator, this x minus 1 definitely cancels. You don't even have to waste time expanding this, since this one cancels with that one. So you just remain with this over this. Once you remain with this, then when x is 1, what happens? Would this one be analytic or non-analytic? This would be analytic. It is obvious that the denominator will not vanish. So x not equal to 1 at x1, this one will not disappear. It remains defined. Then we try the other one. If we try the other one, what happens? There we go. Okay. For this one, since, I think we've done the other one here. Okay, it is here. I have not seen this. This is x minus 1 squared. So you square this for this, and then you simplify. When you simplify, remember there was an x minus 1, which cancels with that x, the power. You go and simplify, you will come up with this one here. Here's my pen. Okay, you'll end up with this one here. And when you end up with this, remember it is at x not equal to 1. Since it is at x not equal to 1, when you substitute 1 here, this will give you 0. But having 0, that is still defined. And since this is defined, the second one, and this one was also defined, we conclude that that one will be a regular singular point. The other one, one of them was non-analytic, and we concluded that it was an irregular singular point. Then after that, you go ahead and you consider x equal to minus 1, which is the last one here. And you do the same analysis. And when you do that, you come, you dilly-dally with it here, blah, 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 blah. You conclude that x naught is equal to 1 is also a singular point. And from that, you can go and you flex your muscles here. Instead of gossiping, you can come and you do this and this. And then once you practice this, you'll be ready to go. By the way, it is very bad for engineers to gossip. Some of you, even when we are having lectures, you are gossiping. And I wonder whether you will really be engineers of really some good standing. In my mother tongue, we say that a tree which will become a movable, you will tell when it is still young. So some of you who keep gossiping during lectures, you are murmuring, you are doing this, you need to jack up a little bit. Okay, I don't know whether there are questions. I want to go to the chat room. You saw a hand. Okay, chat, what is there? On checking the subject after simplifying, okay, this is who? This is Mr. Wafula. Let me check quickly. On checking, I substitute for x naught. After simplifying, still I use the same value. Okay, now okay, all right. That's the same question I've been crying to ask. Oh, hopefully you've stopped crying. Mr. Kasiri, are you still weeping or it is now okay? Cassidy, I would want to hear from you. Hopefully you are okay. Henry?
It is now okay
Cassidy?
now that you are going to answer.
Sorry?
If you are going to answer, it's now okay.
Okay. Then I see some people raising their hands. I don't know who these are. Let me check. Okay, I see hands up, but I don't see these participants. Okay, those who have raised their hands, you ask your questions. Because I want to change gears a little bit. Those who had their hands up, maybe they were stretching their hands. Okay, let's continue since they have decided to keep quiet. Right, let's move on now. Power series solution about an ordinary. Now we know what an ordinary point is, guys. Now that we know what an ordinary point is, we have understood an ordinary, a singular, irregular, regular. We know what is analytic, non-analytic. We can now get down into actual business. Those were preambles, but all examinable. Okay, now here we want to use these power series to solve. Here, the beginning part, I've already illustrated this. We are saying, how do we solve a differential equation? This is where I started. And then one of your colleagues was wondering what was going on. So I'm not going to repeat this. I've already told you this one we can use to solve. And since you can use it to solve, then how do you unify those indices? We have already looked at that. That's where I started. And since that was where we started, it is necessary I go on. We have looked at this equation. Hey, this is good. We continue. There is an example here. So now we want to solve. So we have a very simple system here. Let's solve this system. So what we have is something like this. You see? So we are saying we want to solve this equation. Find the power series solution of the differential equation. This is y prime plus xy, which is 0, about x will equal to 0. When we say about x will equal to 0, it means x naught here is 0. You have to interpret. So what is the general representation? We are saying find the power series solution. So remember we said our general representation of a power series is this one here. This is where we start. Now I'm going to use all that we have been discussing. And I would expect that by now you guys are very alert. Please, you be alert. Some of you who keep gossiping during the lectures, you better pay attention. So we are saying, if we want to solve this one here, that is y prime plus xy is equal to 0. About x is equal to 0. We are getting a power series solution for this one here. So we substitute. If this is y, it means we have to differentiate this y. And when you differentiate this y, what do you get? First of all, since it is about x is equal to 0, it means you substitute. This x naught here is 0. Because this x naught is 0, you get y, which is the sum an x to the n, which is this one here. Hopefully we are together, guys. So we are now not going to differentiate this, but we are going to differentiate this. Why? This question here is about x equal to 0. So throw in a 0 here, you get this one here. Now differentiate this one. When you differentiate this, it gives you this one here. The differentiation, you are differentiating with respect to x. This is n x to the n minus 1, which is this one. After doing that, substitute into the equation. I think I am clear there. When you substitute into the equation, you get this one. The gossipers. Those people who keep gossiping, hopefully you are following. So we are substituting into this equation here. If you substitute into this, the y prime is this one here. So when you substitute for y prime, it is this one here. Then x, the x is here. Then y, the y is this one, which is that one. I think we are done there. Now, we go back to where I started. before that lady who asked, what are we doing? I remember her asking with the attitude. Now what we are doing is this one here. The lady who asked what was going on. This is what was going on. Since we have this, if I call this, I'm now talking to that young lady who asked what was going on. I'm emphasizing. If we call this one equation 1 here. Now, when you look at this, we have already substituted into our the differential equation. The x is here, this is this is here. So first of all, we can start with this one here. Since this is x to the n, there is x here. This x can enter into the sum here. So you have x to the n. Then, of course, this is x to the 1. These, indices. Since the base is the same, you add the powers. That gives you this term here, which is x to the power n plus 1. So this x has entered inside. That one is clear now here. So this becomes that. Now my interest is in this one here. So from here, okay, I'll try to go back to my, yes, okay. So we now are moving from here to here. So how do we get from here to here? This one has been simplified. This is x n to the power 1. But now look at this one here. This one runs from 0, but this one runs from n is equal to 1. These two are not the same. We cannot simplify them. These can only be simplified if the sum, both of the sums here run from the same value. This is from 0, this is from n equal to 1. Give me a second, Dr. Nakakawa. You've already substituted. No, we can work with it, I think. Okay, let me first finish this, guys, then I come. But it will be okay. So they have not yet responded. The editors have not yet. Okay. Kaziji, I'm finishing at 5. Yes, something like 30 minutes from now. Oh, oops. Okay. Yes, guys, hopefully you are there. Mr. Malindwa, can you say I and I continue? Malindwa?
Aye.
Aye.
Okay, good. Let us continue. I thought you can now mute yourselves. Let's continue, guys. So, sorry, I had that small interruption. Okay. So I was saying that we have exhausted this. We now know how this comes to that. Now we are looking at this. So the motivation here, so the motivation here is from this to this. Remember, this is n0, and then this is n running from 1. So since this n is running from 1 to infinity, and this is running from 0, this one here, we need first of all to unify. But remember, sometimes when you unify these series, you may find the powers changing. Now, I want this one here to run from 0. You see this one runs from n equal to 1. But I want it to run from 0. How do I take this one? Since this is n equal to 1, I know that since this power, and I've told you already in that illustration where that young lady was asking what was going on, I told you we start here. So if I have my m, and I say my m is n minus 1, you see that? This one, I'm referring to the power here. Then it means what is m? But remember, n runs from 1. So since n runs from 1, it means my n is 1 minus 1, which is 0. M becomes 0 if I substitute, if I start from n equal to 1. So, but remember, M is N. This one I discussed today. So since M is 0, but M is N, it means this N equal to 1 becomes N running from 0, which is this one here. I think you see it, that one there. Okay?
Pardon on that.
We get back here. Please mute yourselves, guys, unless if you have a question. But you first mute yourselves. I finish this, then you ask. Because some of the questions you may ask, I may preempt them along the way. All right? So I request that for now, I guess that as I go through these notes, rather this lecture, you have some paper. You can keep jotting down your questions. Those who want to type them in the chat room, you can type them in the chat room. Then I finish this, then you ask your questions, because I suspect from what we heard from those other people, as I moved on, somehow people got answers to their questions. So give me a chance to finish this, then you ask your questions. Okay, so I am saying if this gives us that there, we now want to unify this. You can see that from here, everything runs from 0. But now, when we differentiated this, we got N here. But we need to rethink this. Since N minus 1, we are saying M is N minus 1. It means now the N minus 1 becomes N. You can see this is just X to the N. So what was, maybe I change the colors a bit. I don't want to lose anyone. Where is my errors? There you go. Okay. So I am saying, here we go. I can take this one. So you can see this power here, the N minus 1. This N minus 1 has now become N. You can see that one there, this N here. So this was X to the N minus 1, but remember I've told you M is N. So when I say M is N minus 1, it means where we have N minus 1, it becomes M, but M is N, which is this one here. I don't want to change the notation. Then our interest is in how does the AN become AN plus 1. That is simple, it is from here. This is M is equal to N minus 1. But what is N? N is, if I make N the subject here, it will become M plus 1. Remember, M is N, so it is N plus 1. So it means what was AN has now become AN plus 1. But remember, there was an N here also. But what is N? This N is the M plus 1, which is N plus 1. So it means this N here has become this N plus 1 here. That is this one here. So this N is that one there. The N plus 1, I've already told you. If N is N plus 1, that means this becomes N plus 1. And the whole thing runs from N equal to 0 to that. Okay, I will pause and you ask questions. Anyone who has not understood that step before I proceed. I want one who has not. Okay, maybe I go in the chat room first. What is in the chat? Oh, yeah. Okay. Yeah. This is Madam. Okay, I think this is a guy. Sharif, you got. Isn't there any case when both of them are not analytic? Yes, it is there. If both of them are not analytic, then it is irregular. Okay, that one finished. Tumwesije. For me, the example of the power series solution about how do we know that x is 0 is an ordinary point without checking it with the DE, and also if check is done, how is it done? Because we have only seen how it is done for A second order, yet the DE in the question is a first order. All right, that is okay. Excuse me, a little staggered. If M is this, at M is N, A, what is that? Again, N is 1, please help. That is Mr. Wafula Eric. All right, Mr. Wafula, have I answered your question along the way? This question you asked it some time back, but I am hoping maybe you are somewhere now. Wafula. Wafula has disappeared.
Actually, I'm a little confused on the point.
So here we are saying that someone asked, why it was Mr. Yiga, hopefully. I think I'm forgetting some of the names now, but I think it was Yiga. Yiga asked that how do we, I don't know whether Yiga was referring to, I don't know whether Yiga was referring to the question up here. Where? I think his question was somewhere here. I don't know. I did not really understand Yiga's question, but he said, how do we tell that x equal to 0 is analytic? That one we have discussed. Yeah? So he says that there we are given a second order. Yes, we use the second order, but it could as well be a third order, and it could as well be a fourth order. Please, you go and you revise what we did in engineering math 2. I had that equation, and then I also had the illustrations for equations that exceeded the second order. That is, I think, Mr. Iga. Then somewhere he jumbled it, I think was wondering if this is this, about x is equal to 0. I didn't really get him very well. Other questions? I welcome questions. I wish you guys who are typing in the chat, you would ask and I hear the questions. Okay. Do we at the some point assume M is N after? This is who? Yes, Mr. Wafula, yes, you are right on that. Do we assume? Actually, we don't assume. You see, it's not an assumption. Remember, we are in N. If we keep changing, so it's like if N is K, and then if K is say Q, and then if Q is R, we don't want to mess up the computation like that. Even if you are to write an algorithm for this kind of scheme that solves these series solutions, sure, you'll have to come up with one. Otherwise, you'll end up with a code of 1 million lines. So it's not an assumption. I am saying if N is M plus 1, then we do the necessary substitution. Remember, so I can maintain that same N. Otherwise, if you want, you can just take it to M, and then you rewrite all of these in terms of M. You'll still come to the same conclusion, Mr. Wafula. But otherwise, it's better to take it the way you have concluded it down there, that we can just take M equal to N after, which is good. So I like the way you have thought about it. That's the way I'm putting it. Right, then I'm now back, of course I was not seeing, okay, M anyway, all right, Mr. Wafula is back. Good for you, and good for me as well. Okay, I think there are no questions. The gossipers, I think everything is okay. You know, some of you don't ask, and then you start gossiping later. Questions? I think there are no questions. Yes.
Excuse me, sir.
Who is this?
You skipped my question. This is Cassidy Henry.
Yes, Cassidy, what was your question?
I don't know if I'm taking you back, but I'm sorry. On the other numbers which you did first, where you had x minus x naught into a1x over a2.
Now I am very fine. You are taking me back there.
Because someone asked a question and you did answer. You go back.
What you are doing is actually bogging me down. Quite understandable, but not very good. All right. Here, where? Here?
Oh, down, there, somewhere. Like when you're analyzing for x equals to 0, those poles.
I'm listening.
Yeah, at first, when you put like for the poles where you have discontinuity or singularity, then you say x not equals to 0. So you substituted x not equals to 0 in the first expression where you had x minus x naught, a1x over a2x.
Yes.
But then even in the final expression, when you want to conclude that it is analytical, maybe at x not equals to 1, you're trying to show us that x now is 1, yet we don't have x naught anymore, but you're concluding based on x naught. So I don't know how you're doing this.
No. Remember, this is, of course, this one I took it to be 0 because, okay, with respect, if we start with, where is it, the one where we dealt with the 0? Is it this one? I think it is somewhere, I think this is it. For example, here we took x. I wanted to use the very example. I think this is the one here. Yeah. Yes, so you take 0 here, this was 0. Remember at x naught. Yes, but remember when you look at the range and the domain, human, where is my pen? This is a number line, isn't it? So you have all of these. Remember when we started this, the only numbers to worry about were 0, 1, and a -1. If you recall what I said here, I said except, here we said the functions, they are defined for except. So here we are saying if you move from minus infinity to infinity, so you have some x, which is between, this is positive infinity. Of course, you can, if you put this in a set builder notation, you have to write it a little bit better because this excludes 0, 1, and -1. Is that okay? We already know this one from what we have checked here. But since this one was already making a threat, it is better you just substitute that very one that is threatening. We said except for these ones here. So it means if you move,
my issue is you are using that 0 2 times.
Yes, and that is what I am explaining, younger man, that if you move from minus infinity to infinity, we are already saying we are worried about these ones here, isn't it? So I don't have, because from this, you want me to substitute 2, then I substitute minus 1 million, I substitute, I cannot exhaust this. So since these are the points of concern, and I'm looking at it at x will equal to 0, I am better off just checking that very 0 there, which is one of the things I must be mindful of, because I cannot. So, okay, now if I say, okay, let's test x will equal to 3, definitely this one will hold. Why? Because in the first place, it was already holding. You get what I mean? So I don't have to test and I cannot exhaust these ones. So since I had tested for 0, and I've already substituted that this x naught is 0, and I simplify it to something like this, anything outside 0 that I substitute here will be valid for this thing here. But the question is, what was I worried about in the first place? It was 0, 1, and -1. So it is logical to simply throw back that very 0 there.
Okay, I get it.
I don't know whether you understand me, because when we say except, it means on this, in this big range here that you cannot even exhaust. These are the only numbers to worry about. So if my x naught is 0, I simplify it to this one here. But this one can be tested on this number line here using any other value. But I know when I throw in 3 and I throw in -100, you'll ask me, why not -300? Is that okay? So I don't have to go into that. Since this is the number I am worried about, then let me simply again test that here. And you can see when I test that here. So assuming we had taken 3, we would conclude that this is analytic. I don't know whether you are aware. But remember, you would conclude that it is analytic, but you have a x here, which makes again this thing an analytic. So it's better you again test using that very value. Am I clear, Mr. Kasiria?
Yes, you are very clear, sir. Thank you.
Hopefully. Okay. It's good I went back. Maybe we helped some other people who were also being quiet. All right.
Excuse me.
You guys, I need
Excuse
to
me.
number. You are going to ask your question after I have finished. I'm going to pose the questions here because I'm remaining with the 12 minutes. Okay, let me first finish the question I was doing. Otherwise, time will catch up with us and the thing remains hanging. Please, on the pretext of not sounding rude, whoever was asking, kindly allow me to finish the number I had started. Okay, so we had started this and we had ended here. We had ended where? Here, I think. This is what we stopped. This is where we stopped, I remember. Okay, so I had showed you how you move from this one to this one. This one I had already showed you how you get into this. So this is what we brought here. This is actually this one here. Then I have demonstrated how this becomes this one here. And people asked, and I think they exhausted their questions. So now from here, we are heading to here. We are saying that this implies this one here. But the question is, how do we get this? This is very simple. So we want to solve, but now, just look at these two. Look at this one here. This one here is x to the n. Remember, I told you how do we solve? We make these things look similar. So this one is from 0, this one is from 0, but the problem is the powers. This one is x to the n, and this one is x to the n plus 1. That is kind of a mess for us. We need to unify these powers here. How do we do that? That is what I am going to discuss now. So if you look at this here, so all we want is this from our definition. We want this to be x to the n. So since we want this to be x to the n, we must fix this one here. So if I clear that, then I can think about this one. Okay, now let me not circle the whole thing. We are going to concentrate on this one for now. And why are we concentrating on this? It is because of this power here, which is n plus 1. We need to think about that. So how do we think about that? Then again, we say, if our m is n plus 1, hopefully you are with me. I don't remember the name of it. It was Wafula. Wafula, you must be more alert now, my friend. Mr. Wafula, hopefully you are sober. So if this is n plus 1,
I'm there.
we're saying m is now n plus 1. Remember, m is n to avoid over substitution. So if I take this to be n minus 4, if I take the n plus 1 to be m, so if my m is n plus 1, it means I'll have x to the m, which is n. That is this one here. I think you can see this part here. So what does the an become? So I make n, if m is n plus 1, this is n plus 1, I make n the subject. N becomes m minus 1. Or if you want, you can say n is n minus 1. So my n becomes m minus 1. That's why you see here, what I had as an, if you look at this part here, an, the an is now an minus 1. So an has become an minus 1, which is this one here. Hopefully I'm clear. Where does that come from? It comes from this. M is equal to n plus 1. I make n the subject. N is m minus 1, but n is m. So where I had the an, the n becomes m minus 1, but m is n, which is n minus 1, which is this one here. All right? But now before that, remember we have said n is n plus 1. So if m is n plus 1, but remember n runs from 0. Guys, look at please try to look at the sum here. We are summing from n equal to 0. Please mute yourselves, guys. Mute yourselves. We are moving from n equal to 0. Since we are moving from n equal to 0, this n equal to 0 here, we have m, but n is 0. So if this n is 0, what becomes m becomes 1. M becomes 1. And that's why here now our n runs from 1. You can see here it was running from 0, and here it is running from n equal to 1. How have we got that? M was n plus 1, but here we are summing from n is equal to 0. So if n is 0, m becomes what? M becomes 1. It means now we are going to run from 1. Therefore, n runs from 1 to infinity. What was n? Remember we said the m is n plus 1, but m is n, which is n plus 1. So this becomes n plus 1, x to the n, which is this one here. I think we are clear there. And if this is the case, we now have a new system, which is this one here. This system is quite similar. So now what is similar with respect to the previous one? The previous one is the one in red. This is the previous one. Look at the previous one and look at the one in green. This one was n. We have not done anything on this one here. It is this one here. So this one here, we have succeeded in changing the n plus 1 to n. These things I demonstrated in the beginning of the lecture. That is where the lady was asking, what are we doing? Now you can see the use of what I was saying, which is this one here. So if this is the case, we now have the xn and the xn. We are remaining with just a very small problem that can be easily be fixed. And what is that small problem? Since this is n running from 1, we need to upgrade the first one here. So what are we going to do? What we are going to do is to upgrade the one in blue. You see this one here has to be upgraded. That one must be upgraded. How do we upgrade it? It is simple. Simply take it. If you throw in here, n will equal to 0. You throw in n will equal to 0. Just throw in the first digit 0. If you throw in 0, it means that this will be 0 plus 1. That is 1. This will be what? This will be A0 plus 1, which is A1. So you have 1 times A1. So this is 1 here. Because n is 0, you get A1. And when you get A1 here, what does that give? So you have n is 0, this is 0, that is 1.